This is Chaitanya. I'm going to explain the frequency response of the integrator. So basically, integrator, we replace the feedback resistance with a capacitor, which in our case is of 100 nanofarads. And our first case, and we get the output in this format, and the gain value is xc by r, where the xc is 1 by j omega cr, and we can observe from this that the gain is inversely proportional to the frequency. So this is a circuit. Now we are taking the power supply 12 volt to activate the to operate the op amp. So it gives 12 volts to the minus 12 volts to the negative terminal of this, which is the fourth pin, and the 12 volts to the seventh pin, and we connected this ground to the third pin, and we used a male to male connector to use the other wires so that we can make this ground, and we gave input to the resistor and connected it to the second pin of the op amp, and we connected a resistor across the pin 2 and 6, and we took the output from the 6th pin and connected the other terminal to the ground, and we got the output. And this is our output for the combination of 1 volt peak to peak of the frequency 1 kilohertz for the sine wave. So we can see it for the same frequency and same to peak to. Now we are making it for the square wave, so we can see that we got a triangular wave. So our integrator circuit is correct, because the integration of the square wave, the constant, is a linear function. So that's what we got there. So these are the voltage gain values for the respective frequencies. We can observe a decreasing trend in that. This is for the combination of 1 kilo ohm resistor and 100 nanofarad capacitor, and after operating the same for the 2.7 kilo ohm resistor and 100 nanofarad capacitor. These are the readings. This is the graph we plotted from the data obtained. We can observe the voltage gain is getting decreased with increase of frequency. We can observe after a certain frequency the graph is becoming flat, which indicates the op amp has obtained the saturation state. This is the graph for the other combination of resistor and capacitor. We can observe the similar trend of the graph, but we can observe that the gain is a bit reduced a bit because of the increase in resistance. That was question number 1.
Hello everyone, today I'll be explaining the differentiator circuit. So this is the circuit diagram of a differentiator circuit. The only difference between a differentiator and an integrator circuit is the change of the resistance and the capacitance. So in an integrator circuit, we see that here a capacitance is added and here a resistor is added. But in a differentiator circuit, this is the complete opposite. By using the equation of Q is equals to CV and differentiating it with respect to time, we get the current as to be minus V out by R. After multiplying with capacitance and a final output, we get as V out is equals to minus RC dVn by dt. From here, we can easily calculate the gain, which comes out to be minus R by XC, where XC is the impedance of the capacitor. Simplifying it, we get it as minus j omega CR. Minus sign indicates that there is a phase shift of 90 degree. Omega C and R indicates that the gain is proportional to the frequency of the input wave. It is proportional to the capacitance of the capacitor and the resistance of the resistor. So we are giving 12 volts of voltage input through channel 1 and channel 2, and we are going to check the output across pin number 2 and pin number 6. So the output is measured across pin number 6 and we have connected a resistor across it. Then in series to it we have connected a capacitor, and we are giving an input of sine wave through the in series to the capacitor. To pin number 7 and pin number 4 we are giving the voltage inputs through channel 1 and channel 2, and we have connected the ground to pin number 3. If I that our circuit is correct, we are giving an input of a square wave of frequency 900 Hz, and this is the resulting output. Now in a square wave, when the voltage is constant, at that time in the output wave we should get nothing, and when the voltage is suddenly changing, at that time we should get a peak. So this shows that our output wave is correct. Now we'll be doing for the sine wave. Now we have put the frequency of 900 Hz, and the output is similar to what we got in an integrated circuit. The only difference which we get in the readings is that as we increase the frequency from 200 to 10,000, there is an increase in gain. This is because the formula for gain in a differentiator circuit is minus j omega RC. Now as we can see, as we are increasing the frequency, omega is increasing, R and C is constant, that is why the gain is increasing. Now this is the values which we obtained for the 1 kilo ohm differentiator circuit. So at 200 Hz we are getting a gain of minus 11.3, but at 10,000 we are getting a gain of 22.516. Similarly, we have done for 2.7 ohm at 200 frequency Hz. The gain is minus 2.95, but as we increase it to 10,000, our gain comes out to be 26.44. Now as you saw, the gain in 2.7 ohm at 10,000 was 26.44, but for the 1 ohm it was 22.51. This is because, as explained before, the gain is proportional to resistance. So we increased the resistance from 1 kilo ohm to 2.7 kilo ohm. So we got an increase of almost 4. So we have plotted the graph between frequency and 20 log V0 by Vi. So we have written a small MATLAB code, and this is the graph which we have obtained. So as you can clearly see from the graph that as the frequency increases, the gain increases, and after the frequency goes above 10,000 or above threshold frequency, the op-amp will start saturating and we'll get approximately same values. So now we are plotting the graph for the differentiator circuit with 2.7 kilo ohm resistor. So as you can see, the values have increased on the y-axis, but after a certain value, which is at x equals to 6000 Hz, the gain has stopped, the op-amp has started to saturate, and we are getting almost same value at 7000 Hz, 8000 Hz, 9000 Hz. That is all about question number 2. Thank you.
Hello, my name is Ayushavi and I will be explaining the question number 3. We have taken two input voltages V1 and V2 and two resistance of 20 kilo ohm. Two input voltages 1 and 2 and two resistance in parallel lines. Then we add a IC with a feedback resistance of 10 kilo ohm. The output of this voltage is input for the resistance, and this is the feedback resistance of another op-amp. This is our circuit we made. This is the output resistance, and here we get the output for this circuit. And the average of these two sine waves which we give here, the average of these two sine waves which we give here in first channel, we give 1 kilohertz frequency with 1 volt peak to peak with 0 phase, and in channel 2 we give frequency 3 kilohertz with 500 millivolt peak to peak in the same phase, and we got the output like this. And here is the mean we got like this. And here we give the input to the op-amp 12 volt positive to pin number 7 and negative to pin number 4. And this is our complete circuit which we show the two op-amps and the resistance. For channel 1 the starting phase is 0, and for the channel 2 starting phase is also 0. And here blue is the input of channel 2 and yellow is the resultant wave. And it is all about question number 3 and it is thank you.